I am very happy to present you the academic trajectory of Dr. Pierre Legrand. He received a PhD in applied mathematics in the multifractal analysis and signal processing from the École Center of Nantes and from Nantes University in year 2004. During his thesis, he developed interpolation and denoising methods based on the Hölderian regularity and wavelets. Additionally, he was in charge of the development. Year 2005, he received a postdoctoral position shared between Citedi in Ensenada, Mexico, and the INRIA complex team in France. In 2006, a second postdoctoral position allowed Dr. Pierre Legrand to develop the first genetic algorithm running on a pocket PC for the development of new methods to parameterize cochlear implants using interactive evolution. On year 2006, he became a researcher at the IMB, which is the Institute of Mathematics from Bordeaux. In year 2008, Dr. Pierre Legrand started to develop and apply signal processing techniques and evolutionary computation methods to solve for the analysis of EEG signals. Since the year 2010, he is also a researcher at INRIA in the ALEA and CQFD research team. So please welcome to Dr. Pierre Legrand.
To be here. Is it possible to just shut down a bit the light? Thank you. Thank you very much. In fact, this talk today, it's not only science, it's also a true story. We'll talk about artificial evolution, fractal analysis, and applications. And the second part of the title is 10 years of collaboration with ITT. I should say 10 years of collaboration with ITT and Citedi also, because we had application collaboration also, a strong one with Victor Diaz and Enrique. Okay, so during the last years, I had the opportunity to participate to a research project. So some of them are here, but especially one is very important for me. It's this one. It's a European project that we had with ITT, with 4 countries: Spain, Portugal, Mexico, and France. Or countries. It means that students from Mexico were able to go into France and to Spain, etc., etc. And so with this project, during 3 years, we wrote 31 journal papers, 28 proceedings, 2 books, and we had more than subject. We manipulate theoretical tools. Some of them are here. And we try to mix them to build new tools. And sometimes we also contributed to those areas. It's what you have here. We tried also to combine this with software, actually biomedical applications. And we were very lucky during this time in this project because we had very bright students. And it was really a pleasure to work with them. And what you see is, it's a big collaboration. Of course, I will not have the time today to present all these blocks, of course. So those are the Mexican blocks, I mean. So I will just take those ones, okay? And if you have questions, of course, I can come back on the other contributions. Okay, so give some definition on artificial evolution, and I will give 2 contributions. The second part will consist on some reminders about the Eulerian regularity. And finally, in the part 3, I will show 2 contributions related to these 2 topics. Okay, part 1. So I will start by talking about artificial Darwinism. Artificial Darwinism is stochastic optimization, which uses mechanisms inspired by the biological evolution, such as the reproduction, the mutation, the selection, and the survival, genetic programming, but many others, okay? I will just focus on those 3 today. For all those algorithms, you will have the same ingredients. And those ingredients are a population of potential. All these algorithms, they also share what we call an evolutionary loop. In this loop, you have an initialization of potential solution that we call parents. They are evaluated to get the result of your optimization problem. This is an example of the maximization of the function f function. So we are looking on this axis. Where is the place where you will find the max? So at the beginning of your, at the first generation of your algorithm, you will have an initial random population. So you see those red dark max of your problem. Okay. I will just give few definitions. First, what we call genetic algorithms. Sorry. You have already heard about genetic algorithms. These algorithms are from the 60s, and in the canonical forms of this algorithm, you will find what we call the locus crossover. You have 2 potential solutions here that we call the parents, the father, the mother. You select a random position here, and then you cross and you switch, and then you get 2 children. And the canonical mutation for the genetic algorithm is the binary mutation. With a certain probability, 1 gene will mute, a 0 will become a 1, and a 1 will become a 0. You also have the canonical are working usually with vector of real value. Then the crossover and the mutation are not the same. They could be, but in the canonical form of those algorithms, they are not the same. What we use usually is, for the crossover, is the barycentric crossover. It means that you will build a child in the middle of the father and the mother, in the middle, somewhere between them, and you will apply a Gaussian mutation. You will just add a random variable with a certain probability and with a standard deviation sigma. Evolutionary strategy, because usually I mix them. I do not use canonical forms of those algorithms. I mix them depending on the problem I try to solve. You cannot solve any kind of problem just by doing like a black box and launching your algorithm. You have to know what you are doing. So that's why you almost never use the canonical form of the algorithms. Okay. I will show you a short demo, so I have to switch between the computers. If I found the cable, this one, no. No. Is it plugged on this computer? Yes, I'm just looking for the video cable. Yes. Okay, so it's a very simple example. Very simple. It's like between 15 and 20 minutes of coding. Okay, I will try to show you an example of minimization with a genetic algorithm, and it's not. As you see, this fitness landscape is very hard, very complicated, so it would be very hard to minimize. This is the contour plot, and the solution is somewhere inside of those blue rings. This is your population of your genetic algorithm, and it's evolving, and we hope that we will find the optimum. Yeah, I'm a bit confident with it. Okay, as you see, we reach the minimum, and this is the minimum is at 0, 0, so it's fine. And here is the trajectory of the best individual generation. The second example is a very well-known problem. Alors, this is a the salesman travel problem. The objective is to find the shortest path between cities. So what I will do, I will generate randomly cities in a map, and I will try to find the best path. So the position of the cities is random also. Okay. So randomly, I obtain a path of 3,600. This is slow because I print it, okay? But if I don't put the figure, it's instantaneous. Okay, and look, we're at 1,700. Okay, we can go more. I stopped at 750 generations. Okay. Okay, so do you have questions on those examples? So after this short demo, I will finish those definitions with genetic programming. When you are using genetic programming, you do not need to know what is the shape of your solution. Your algorithm will build your model. You don't need it. It's like the other evolutionary algorithm. You have an initial population, a new bet. In this case, you do not manipulate reals or binary string. You manipulate trees of functions. For example, here, what you have is the function that map x plus x divided by x to x. Okay, this tree represents a function. And then this kind of algorithms are very well suited for symbolic regression. Let's say that you want to find this blue curve here, but you just have the blue points. It's what we call the fitness cases here. We have the blue points, and we want to find the curve, in your program, excuse me. You will have individuals, you will manipulate individuals, which are function, like this red one, and you try to get as close as possible as the blue one, as the blue dots. Okay? But you will see more this afternoon about genetic programming. This is the first contribution I want to present to you. This work is related to the Institute of Technology of Tijuana, and she did a very great work. Not only this, but she worked on many contributions. So I'm very happy to show this work, which has been carried out with Leonardo Trujillo and Edgar Galvan Lopez. So evolutionary computer to be able to grade each problem based on this difficulty. Of course, this difficulty will be related to the tool that we will use to solve this problem. In our case here, we will use genetic programming for classification that the problem poses. We know two groups. The first one is what we call the evolvability indicators, that they focus the analysis on the fitness landscape and how the fitness landscape relates to the difficulty of a search. You remember my first demo? You saw the landscape. And the second kind of work to determine the difficulty that the problem poses is the predictor of expected performances. This kind of problem tries to correct this kind of tool, try to characterize the problems based on the characteristic of the problems. We take the problem, we try to extract some characteristics, and okay. Why we focused on the prediction of expected performance? Because in this case, we do not need to execute the program. If we have to run the program to know if it's efficient, so what is the goal? If you run it, it's done. It's not necessary to know if it will be efficient or not. And finally, a preliminary work by Juliana showed that the correlation between the EI, so the evolvability indicators, and the classification rate is not so is worse than the correlation of the PEP with correct classification rate. So we'll go for PEPs. She built a set of classification problems artificially, and then for each of them, she divided it in two parts. One part for the training, one part for the testing. And then she applied the classifier she wants to evaluate on this problem. Then she obtained an average classification error for this problem that we call CU mu. Okay, and she did it for all the problems she built. In parallel, she extracted features from each problem. And then she built the fitness cases that we have here, the pair beta CU mu. And with those pairs, she made a symbolic regression. And with those pairs, she built with another GP, with another genetic programming, she built a model, PEP, just by symbolic regression. Then, when you face a new problem, you extract the characteristic of the problem, you put them in the PEP model, and so the feature proposed was first the geometric mean, which measures the homogeneity of covariances of classes. The second one is the feature efficiency, which measures the amount by which each dimension will contribute by the separation of classes, and then you take the max of those values belongs the dimensions. The third one is the class distance ratio, which is the ratio between the average of all intra-class distance divided by all the mean of the interclass distances. The volume, and finally the Canberra distance, which provides a numerical measure of distance between vectors in a space. And we used for this Canberra distance three quantities. The first one is the first quartile, the second one is the median, and the third one is the third quartile. Okay. So we have our criteria, we have a protocol. Now we have also to build synthetic problems. Those are synthetic classification problem ordered by difficulty. This one is the simplest, this one is the hardest, and we computed the rate of classification, the rate of classification error. Sorry. Okay. Given criteria I showed a few minutes ago, and the classification rate. As you see some correlation, but not very good correlations. Okay, so we see that not any of those criteria is able to classify, to help us to characterize, to characterize the difficulty of a problem. Okay. So what we propose is to build three kinds of PEP, predictor of performance, three kinds. The first one, we use the four best correlated criteria. The second one, the 5 best correlated criteria. And the final one, all the criteria. So I come back on this protocol. We build those problems. We compute for them this PEP model to new problems. And we will try to get prediction of the errors that we will obtain if we apply this PGPC classifier. Okay. These are the results that we obtain on on synthetic problems. On the abscissa, you have the number of the problems that are ordered by difficulty. In green, this is the ground truth. These are the true classification error rate. And in orange, it's the prediction we obtain. As you see, the predictions are good. I think they are good. And if you look at the correlation on this plot, because here you have the classification error, and here in ordinate you have the predicted classification error, you see nice correlation between the ground truth, which is the classification, the error rate of classification, and the prediction. Okay, so we learn on artificial probes. The results are not so good. Okay, it's the same. The problem are ordered by difficulty. You see that for the simple problem, our predictor is working quite well. On very difficult problem, it's working quite well also, but in the middle, it's not very efficient. Even if the correlation are not bad, we reach 0.8 which is a good result. But we want to improve it. We think that we can improve it. Then we propose the specialized prediction of expected performance. And what we will do, during the process of learning, we will sort our problem based on their difficulty, on their ground truth difficulty. And then we make difficulty problems, and the last one, hard problems. But we could decide to divide it in 4, 5, or just only 2. For each class, we will build the PEP model. And in parallel, we will, with supervised classification by GP, for example, we will build a model, a PEP selector, which be able to tell, based on the beta, in which class is the problem. So we built something more complicated, but more efficient. When we have a new problem, when we face a new problem, we extract the beta vectors, or the criteria. We use the PEP selector. The PEP selector is a difficult problem. And then your PEP model will give you the prediction of the error. Okay? These are the results. We improve a bit the correlation. It's not perfect, but we are closer on the ground truth. What you see here, this black point, it means that the PEP selector did not work well. It selected the wrong PEP. So when you select the wrong PEP, you're lost. If you use the good one, you are exactly on. We proposed a work that predict the performance of a GP classifier, and we were able to build an ensemble of steps for each group to improve the accuracy of prediction. And what is interesting, I think, here is that we could apply this to any kind of problem. In this application, we applied this to a classifier, a genetic programming classifier, but we could use anything else. And more, you will use this other kind of machine learning. I think it's interesting to go further in this direction. And of course, it can be applied not only for classification, but also for symbolic regression problems. Okay, so this was the first contribution. The second one is about the detection of outliers. Okay, I will be fast on this one because this afternoon we will have another talk. I think this will be mentioned also. So this work is related also to the work of some students from the Institute of Technology of Tijuana. Especially, it's related to the PhD thesis and master thesis of Uriel Lopez. And this work has been done with Leonardo, Uriel, Juliana, Enrique, and Sarah Silva. Is efficient for symbolic regression. But what will happen if we have outliers when we do our learning phase? The impact of the outliers are not been studied in depth until now. What is an outlier? It is a measurement of a system that is anomalous with respect to the behavior of the system. Okay, you will find plenty of definition of outliers, but this is one we use for this work. But we will not focus on the data set. We will focus on the data set. Then are they outliers or are they regular data? That is why it is important to distinguish between a given measurement, observation, and the true value of a variable of interest. Okay? That's why it's reasonable for a data set to be, for us, to be contaminated by more than 50% of outliers, because what is important for us is the process. Okay? This is an example of symbolic regression by a genetic program. I'll show you here what is the impact of outliers on the symbolic regression. You have those fitness cases, which are the black points, and this is the real model in black. If you have if you had those two outliers here, your GP will build. We have to solve this. A known method to remove outliers is the random sample consensus. This method is very efficient, and I will show you the pseudocode just in a few lines. First, you will take a random, and from them, you will build a model. Okay, you use the subsample, and you build a model from this. And then you will contribute the residual you obtain on all the data that were not in this. You will compare for each point you will compare this residual to a threshold T. And you will build what we call the consensus set, which contains all the data points which are not in the original sample set, for which this residual is lower than T. The number of elements in the consensus set is bigger than the number of inliers you know, then it means that your model is a good one, so you keep it. If not, you run it again and again, and at the end, you take the model that return the explored by Uriel, was to improve this and to change just the second step and to replace the building of a linear model, for example, by a GP model. Okay? And we call it the round. You extracted. You will not build a linear regression or something like this. You use genetic programming to build an efficient model. And I show you the results just in a few words. This is an example of training data with 90%. If you make a zoom, you obtain this. Okay? The original model is in black, and the big round are the Randstad GP solution. Is the Randstad GP solution. So I think that you will have more information on this afternoon. It's okay for you now? Yeah? Okay. So I continue on the part 2. As I said, I will talk about the estimation of signal regularity. And I will focus on the Eulerian. The Euler pointwise exponent is the most common tool used to estimate the regularity of the signal. Okay, I will try to explain this definition simply. The Euler exponent is the supremum of S for which you will try to find the best envelope around the signal, and the best envelope will have this equation, and the alpha which is here is the Euler exponent. You understand that if alpha is growing, then the envelope addition. Okay, that means that the signal is irregular. So this tool, we used this tool a lot. There are two main methods to. We'll just focus on the second method. Okay. Okay, this is oscillation. The method to estimate the regularity of the signal, the well-known method to estimate the regularity of a signal is based on a theorem from Stéphane Jaffard. This theorem says that if you consider the wavelet coefficient of a signal above a point t0, then those wavelet coefficient will be, okay, this value is less or equal to this value depending of the Euler exponent. And conversely, some of this coefficient will be of this order of this order. It means that from this theorem, we will be able to estimate the Euler exponent just by doing a regression of the wavelet coefficients and a point t0. Okay. I don't know if you are familiar with the wavelet transform, but the wavelet transform will provide what we call a dyadic grid here, which will give an information on the content of a signal for each point. Here you have the low frequency, and here's the high frequency. The signal is at this level, information in the high frequency, this one in the a bit lower frequency, etc., etc. And the coefficient for the low frequency for this point t0 is this one. Okay? So for any point, you will be able to say what is the frequency content. You see that it's more powerful than the Fourier transform because here you have exactly the information on time. So you know where are the frequencies. Okay, based on scales, the scales are here. And then you consider the slope. And from this, it's very simple to write this theorem. We wrote this theorem to obtain the estimation of the regularity. Okay? But as you see, it's a process which is a bit complicated. I will come back on this later at the end of this talk. Just an application. on synthetic signal. It's a generalized Weierstrass that we built with the toolbox FracLab. It's a signal with the regularity, ordinary regularity, which is evolving linearly with time. Okay, so the true regularity is the black line here. It's what we should obtain when we estimate the regularity. And with the regression of the wavelet coefficient, the talk, and now I will try to mix those topics, those areas, to solve real-life problems. The first application is an application on classification of EEG signals based on the physiological states of a person. In the European project I mentioned at the beginning of this talk, and he had the chance also to meet in some conferences the student from the ITT. So this work was carried out with Leonardo Trujillo, Frédéric Feita, Marie Chavant, and Laurent Vézard. Okay. The goal here was to characterize the state of alertness of a person from his electroencephalogram. We wrote a protocol. One kind when the subject is in normal state, that we will say that it's a state of alertness normal. And the second one, when the subject is in a state low vigilance, that we will call relax. So, okay, at the beginning, the subject come into the room. We put on him sensors. We record. We make him relax. I mean, we submit him to a relaxation session, and then we perform a second measurement. This is our system with one of our students. This is the cap we use. It's international 1010 system measurement of 58 electrodes. And to install the 56 Hertz. And the recording time is 3 minutes. So during the campaigns, we had the chance to add 58 subjects. But unfortunately, we had to reject a lot, and we were able to keep 16. The relaxation session was made of 20 minutes with recorded voice, with 3 exercises. The first one is the autogenic training, which is a kind of self-hypnosis. The second one is the progressive muscle relaxation. And the third one is mental visualization. Okay, you have to visualize a place you know, a place you like. So this is a recording before relaxation, obtained after the relaxation session. It's what you see here. It's a puff of alpha waves. It's usually what you see when you are in a pre-sleeping state or very relaxed state. Of course, now we have these signals, and we want to extract features to make our classification. But our problem is very difficult, because we do not want to say for the same guy if he was relaxed this time and not relaxed the other time. We want to know when we have a new subject, we want to know directly if he's relaxed or not. So this problem is very difficult. And then for each electrode, I obtained the dyadic grid, and I decided to sum it on time. Then I lose the time information, but I have the energy for each band of frequency. And then I made a plot. This is for one subject. If you look at the frequency in abscissa and the energy for each frequency, you have something like this. Okay, but we still know that there are some literature on alpha waves. So maybe it was interesting to check those frequencies between 8 and 12 Hertz. That's why I considered those frequencies, and I made a regression. And I was thinking about using maybe this slope as a criteria to make the classification. And finally, we saw something. When you make the sum and you print the slope, you will see that for the relaxed state, almost each time, the slope is bigger than in the normal state. Okay, let's see what happens if we sum it on the electrode and we consider subject by subject. For each subject, it's almost the same. It means that the slope here in the relaxed state is higher than the slope in the normal state. Okay, excellent. It means that if you have 2 recordings of a guy, you can say Okay, this time it was more relaxed than the other time. But you cannot take a line here and say, okay, above this line they are relaxed and below they are not relaxed. No, it's not efficient enough. And it's also confirmed by the result we obtain using, regular, usual machine learning classification method. The results were very bad. So our approach is to design a relevant evolutionary algorithm to solve this task of classification. But more, we would like to find one electrode, because to put the cap is costly in time. We need 45 minutes. In real application, it's not possible. Not any pilot or not any professional guy will allow to use 45 minutes to put a cap. So we will try to find the relevant electrode and to find. This is the genome of one individual of our algorithm. We'll manipulate this vector. The first value will be the number of the electrode. And the following ones is a binary string saying if we use or not a frequency for our regression. This is our population. I take this individual. This individual means that I use electrode 15. Okay, so I take the signal from the electrode 15. I compute the wavelet transform. I compute the energy for each frequency, and then I will use this frequency, this frequency, this frequency to compute the slope. Easy. And when I associate this with classifiers, simple ones, we obtain correct classification rate of 87%. It means that when you have a new person with 87%, you know if he's relaxed or not. This is a mean on 100 runs. If you take the best result on all the runs, then you obtain 89% of good classification rate. And you obtain electrodes. You just need one electrode and just those frequencies. Okay. This was an application so that interested a lot neuroscientists. Is regularity estimation with genetic programming. I told you that there are two main methods to estimate the Eulerian regularity. Here we propose a new one. This work has been done with Leonardo Trujillo, with Gustavo Olag, and Jacques Lévy-VL. Okay, and it has been published in Gecko and also in Information Science. Okay. As I told you, the Holder exponent is a mathematical tool that measures the regularity of a signal around each point. Here you have an image, and here it's the regularity corresponding to this image. It means that for each point you can associate a regularity, which is here. But for of the signal, so you will have to estimate the regularity of a signal. So this estimation is costly. You have to make a wavelet transform, you have to compute logs, you have to make the regression, you have to compute the slope. So it's costly. That's why it's not used in real life applications. So our contribution will be to evolve pointwise Holder exponent, an estimator of pointwise Holder exponent for 2D signal with genetic programming. To build this estimator, maybe we will need 1 week or more. Obtain a few awards for this work. We obtained the best paper award on the genetic programming track in Gecko, and we were finalist in the MIS award in Gecko 2013. And I have to say that it was a huge work of Leonardo Trujillo, a huge contribution. And it was, I think, our first really strong contribution. Very working together like this. And I'm very proud of this work. So thank you, Leonardo, for this. So what we did is we were able to choose the regularity of the images we want to build. There are an infinity of images with the same regularity. Okay. We choose to build a large number of images with a polynomial regularity, a large number of images with a sinusoidal regularity, a large number of images with an exponential regularity. This is an example of the images of regularity. With those images, we build a large number of images. These are 2 examples for polynomial, 2 examples for sinusoidal, 2 examples for exponential. And then we run the GP, and so the result, this is one of the results we obtained. This is a tree. And then we were able to apply this tree on images. And since it was real time, it was very easy to apply. For example, this is an original image. It's what we obtain with traditional method. This one is oscillation method. And this is what we obtain with 2 different GP estimators that we built together. Okay? Usually, when I talk about this, I come with my webcam and I make a movie with the attendees in this computer. So it was nice to obtain those results. Okay, this is the end of my talk. Because it was a real pleasure. Student from ITT, student from Citedi, and I hope that I will be able to continue this collaboration, this strong collaboration we have together, because for me it's a real pleasure. So thank you very much.
Thanks, Pierrick, for this excellent and great talk. A question for the speaker, for Dr. Pierrick. Anyone?
It's very interesting how to use genetic programming for classification. So I have a doubt. How do you are fitting with when you have a data set? So you train first with a very initial set, and then you have another sets. You have a partition for your data set, and first you train your algorithm with
it's like a regular machine learning. You will divide your set in many sets, but usually what you do is to keep always a set never seen before for the validation, and also another set never seen before for the test. Yeah. This is, but it's not always the case. Many options are possible, but it's like regular machine learning in this sense.
Okay. Another question? I have one question, Pierrick. I found very interesting the work that predicts the complexity of classification problems. You mentioned that you can predict the complexity of GP classificators.
You know this block. Just go back on the slide. To see that Juliana is here in the room, so it's a pleasure. Thank you very much. Yeah, here in this block, you put the tool, the method. Okay, for this kind of problem, PGP classifier will be efficient, but maybe it would be another kind of classifier. Here. When we show the step, when we show the step here, maybe here tell you which kind of methods you should use. And then you can imagine that when you have a new problem, you extract just the data, you put it in the system, and the system will tell you, okay, use PGPC, or use machine learning, or use something else. And if the features beta are different, maybe you will have another predictor.
Thank you. have another question. You show us a very wide range of application in where genetic programming is very useful. So I remember from the school the evolutionary computation that starts with simple genetic algorithms, and now genetic programming. In your opinion, which is the direction that this area is taking?
Now, if you what I will say is very subjective. Okay. Now, when you go in a conference of signal processing, for example, like I was in ICASP in September in Spain, for each paper it will be deep learning for segmentation, deep learning for denoising, deep learning for now. Okay, now almost everybody that do not build methods use deep learning. Deep learning is quite old, but it was not used because of the lack of power of the computer a few years ago. And now everybody runs into it because you just have to put your data in and you let it run, and then you build a black box, and it's what we are doing. We have, I think that there are still a lot of things to do in the area of genetic algorithm and genetic programming. And I think that the future is in hybrid systems, to mix tool together, and also to stay close of your application. What I mean by this, I mean that there is no problem, there is no method for solving any kind of problem. You have to know the problem you want to solve. You have to know it to build a proper genome of your algorithm, a proper kind of genetic programming. Will you use multiple trees at the same time? Will you use semantics? You're welcome.
Anyone have a question for Dr. Perry? Come on, don't be shy.
I'm still there this afternoon if you want. If you find a question later.
Okay, so please thank again to. Next, we are going to have a break for lunch, and we back at 4 o'clock for the next.